Welcome to Tech with Kaushik, where we turn fast-moving technology trends into practical career advantage. Today, we are exploring one of the biggest shifts in cloud engineering, the rise of the AI-augmented cloud engineer. This is not another video claiming that artificial intelligence will magically replace every cloud professional. Instead, we will follow a clear journey from manual configuration to intelligent infrastructure, cost-aware delivery, autonomous operations, and finally, system-level architecture. You will see where AI is powerful, where it still fails, and which skills can make cloud engineers more valuable. If you work with cloud, DevOps, SRE, platform engineering, or infrastructure as code, this journey is designed for you. I have also prepared a detailed PDF study guide covering the key concepts discussed in this video. You can download it using the link provided in the video description. Subscribe to Tech with Kaushik and stay until the end, because the final transformation may completely change how you think about your role. Let us begin with the work that is already disappearing. For years, cloud engineers have spent huge portions of the day copying configuration, editing YAML, fixing indentation, and searching documentation for the right property name. That work is useful, but it is not where the highest engineering value lives. AI can now generate repetitive configuration in seconds, explain unfamiliar parameters, and convert a plain language requirement into a strong first draft. Being fast at typing YAML is therefore no longer a durable advantage. But this is not the death of the cloud engineer. It is the death of treating the cloud engineer like a configuration machine. The opportunity is to move from syntax to systems thinking. Instead of asking, how do I write this file? Ask, what should this platform achieve? What did go wrong? Which boundaries must exist? To understand why this change is accelerating, look at the scale of AIOps. AIOps is moving from a specialist tool category into a major part of modern cloud operations. Industry projections referenced in our research place the market on a path towards roughly $32 billion by 2029. The important point is not the number alone. The number represents growing demand for systems that can analyze telemetry, reduce alert noise, identify likely root causes, and recommend or automate safe actions. Cloud environments now include microservices, containers, serverless functions, data platforms, GPU workloads, and AI agents. Humans cannot manually inspect every signal at that scale. Organizations, therefore, need intelligence across operations. For engineers, this creates a powerful career signal. The future is not only about deploying infrastructure. It is about designing infrastructure that can observe, explain, and increasingly heal itself. That brings us to the larger architectural shift behind this growth, the Agentic Cloud. Traditional cloud systems wait for commands. An engineer writes a script, a pipeline runs, and an alert fires after something crosses a threshold. An Agentic Cloud behaves differently. AI agents can interpret a goal, gather context, select tools, perform bounded actions, validate the result, and adapt the next step. Imagine asking for a secure, cost-controlled test environment. An agent could propose the architecture, generate the infrastructure code, run policy checks, estimate cost, deploy after approval, and monitor the outcome. The key word is bounded. Autonomous does not mean uncontrolled. Identity, permissions, policy, audit trails, and human approval remain essential. This changes cloud architecture from a collection of passive services into a coordinated operating system for goals. But for agents to work safely, they need shared context and clear interfaces. First, we must understand the difference between yesterday's reactive cloud and tomorrow's goal-driven cloud. A reactive cloud responds after an event. CPU rises, an alert fires, someone investigates, and a runbook is executed. A goal-driven cloud starts with the desired outcome. Keep checkout latency below the agreed level. Maintain security compliance. Stay within budget. Recover safely from known failures. The platform continuously compares reality with those goals and decides which approved action should happen next. Events tell the platform what happened. Goals tell the platform what matters. That distinction is critical because AI agents need objectives, constraints, and measures of success. Without those elements, autonomy becomes random automation. With them, operations become proactive and context-aware. The engineer's role moves towards defining outcomes and guardrails that machines can execute reliably. A single agent cannot manage every part of a complex platform, so the next step is coordination between specialized agents. Think of the future cloud team as specialized digital operators. One agent understands infrastructure. Another checks security policy. Another watches cost. Another analyses observability signals. A coordinating agent combines results and requests human approval for high-impact actions. The infrastructure agent can pass a proposed deployment to the security agent. The security agent can reject an overly broad permission. The cost agent can recommend a smaller instance. The coordinator can combine those findings into one decision package. This design is powerful because each agent has a focused responsibility and limited authority. It is safer than giving one general agent unlimited access. The challenge is connecting agents to tools and trusted information consistently. That is why a protocol layer becomes important and why MCP has gained so much attention. The next image explains MCP with one simple comparison. MCP, or Model Context Protocol, can be understood as a standard way for AI applications to discover and use approved tools in context. The USB-C comparison is useful because a common interface reduces the need for a custom connection every time. In cloud engineering, an MCP server might expose selected capabilities for infrastructure repositories, monitoring platforms, ticketing systems, or cost data. The agent does not automatically gain unlimited access. The connection still needs authentication, permission boundaries, logging, and carefully designed tools. The real value is portability. A well-designed agent can interact with different systems through a consistent pattern instead of being tightly hard-coded to one integration. This is an important building block for safe, tool-using AI. But enterprises rarely live in only one cloud. The next challenge is letting intelligence work across environments without losing control, context, or governance. Most real organizations operate across more than one environment. One cloud may run core applications, another may support analytics, and specialized providers may supply AI compute. Cross-cloud agent mobility does not simply mean copying an agent between providers. It means separating the agent's goals from provider-specific tools, identities, and policies. The same optimization objective may require different actions in AWS, Azure, or Google Cloud. A portable agent understands a common intent while invoking the correct approved capability for each platform. That makes open interfaces, policy abstraction, and consistent telemetry extremely valuable. It also creates a new engineering responsibility, designing the control plane that keeps agent behavior understandable across boundaries. Multi-cloud autonomy without governance increases risk. Multi-cloud autonomy with permissions, shared observability, and human escalation can reduce friction. As agents handle provider-specific syntax, the engineer's value starts moving higher up the stack. This staircase represents the most important career message in the video. At the bottom is repetitive manual work, boilerplate, copied commands, and predictable alerts. Higher up are validation, platform design, governance, economics, resilience, and business outcomes. AI makes the lower layers faster, but it does not remove the higher layers. It increases their importance because generated work must be reviewed against real constraints. The engineer who only memorizes commands may struggle. The engineer who understands trade-offs becomes more valuable. Why this network design? Why this identity boundary? What is the blast radius? How will the system fail? What does one transaction cost? Those questions cannot be answered by syntax alone. Do not compete with AI at generating text. Become excellent at defining intent and judging results. Our first practical pillar shows exactly how that works. Pillar 1 is smart scaffolding. Scaffolding is the initial structure that helps a team start correctly and move quickly. In cloud engineering, this can include infrastructure modules, repository structure, networking patterns, identity configuration, deployment pipelines, tests, and documentation. AI can generate this foundation from a well-defined requirement, reducing blank page work and standardizing common patterns. But smart scaffolding is not a one-click production deployment. It is a first version grounded in approved architecture. The strongest approach combines AI generation with trusted templates, reusable modules, policy checks, and review. The engineer owns the blueprint, constraints, and acceptance criteria. AI fills in much of the repetitive structure. This changes the unit of work from individual configuration lines to an expression of intent. Let's see what that shift looks like. The old workflow begins with syntax. Which resource block do I need? Which parameter is required? What indentation is correct? The new workflow begins with intent. For example, create a private, highly available application environment. Encrypt the data. Restrict public access. Include observability. Keep the estimated monthly cost below a defined budget. That requirement contains architecture, security, reliability, and financial expectations. AI can translate the intent into an initial implementation, but the result depends on the specification. Vague intent produces vague infrastructure. Clear intent produces something reviewable. Prompt skill alone is not enough. Engineers need domain knowledge to express non-functional requirements and failure conditions. Intent must also be testable. We need evidence that encryption is enabled, the network is private, and cost is acceptable. The next visual makes the productivity difference obvious. On the left are hundreds of infrastructure code lines. On the right is one concise requirement. The message is not that the prompt permanently replaces the code. The code still becomes the deployable, reviewable, version-controlled source of truth. The change is how the first draft is produced. Instead of building every block manually, the engineer describes the desired system, provides organizational standards, and lets AI generate a candidate implementation. That candidate enters the normal workflow: diff review, testing, security scanning, cost analysis, and approval. This can shorten the path from idea to prototype, especially for familiar patterns. But speed creates danger. Incorrect infrastructure can now be generated faster than ever. Review must become stronger, not weaker. The real productivity gain happens when generation and validation evolve together. First, let us inspect what an AI-generated cloud architecture can include. Here, the AI engine turns requirements into structured infrastructure files and a complete cloud design. It can propose networking, compute, databases, load balancing, storage, and security groups. It can also create variables, outputs, documentation, and test suggestions. For a prototype or standard pattern, this can save significant effort. More importantly, it gives the engineer something concrete to review. Treat generated infrastructure like code from a new team member who works extremely fast and sometimes sounds more confident than the evidence supports. Review every permission. Validate provider versions. Check naming, tagging, state management, availability, backup, and recovery assumptions. Confirm that the design matches your actual platform standards. AI can assemble components, but only engineering context determines whether the assembly is appropriate. Once we move from a demo to enterprise scale, 3 difficult boundaries appear immediately. The 3 shields show common areas where generic AI output becomes unreliable at scale: compliance, network topology, and cost limits. Compliance requirements are specific. A control that is acceptable for one workload may be insufficient for regulated data. Network topology depends on existing address space, routing, shared services, and private connectivity. Cost is equally contextual. A technically valid architecture may be financially unacceptable. AI may also invent properties, select outdated patterns, or optimize one component while harming the whole system. Production automation must therefore be grounded in current documentation, internal standards, and executable policy. The right question is not whether AI is good or bad. Ask which decisions can be delegated, which require validation, and which require human approval. A small identity mistake can create a large blast radius. The next slide shows the kind of red flag a confident-looking draft may hide. This code looks clean, but the highlighted permission is the danger. An over-permissive identity role can give a workload far more authority than it needs. The configuration may deploy successfully and still create a serious security risk. This is the difference between syntactic correctness and architectural correctness. AI can produce valid-looking code, but does not automatically know every trust boundary, data classification, separation of duties rule, or threat model in your environment. Engineers must enforce least privilege, short-lived credentials, clear resource scoping, and auditable identity paths. Automated policy can catch known anti-patterns, but humans must understand why access exists. Never approve permission because the explanation sounds reasonable. Ask what action is required, on which resource, from which identity, and for how long. This brings us to the upgraded role of the cloud engineer, the intent auditor. The intent auditor does not merely check whether code runs. The intent auditor compares the implementation with the original outcome. Did we request private storage? Then public access must be provably blocked. Did we request encrypted production logs? Then encryption, retention, versioning, and access control must be validated. Did we set a budget? Then expected cost must be visible before approval. This role combines architecture, security, operations, and business context. AI generates alternatives and explains trade-offs. The engineer decides whether the evidence is sufficient. If this journey is useful, subscribe to TechWithKoushik, like the video, share it with your cloud team, and comment with the task you most want AI to automate. We are moving from generation into the part that makes production AI trustworthy, automated guardrails. Pillar 2 is shift-left guardrails. Shift-left means moving feedback earlier in delivery, before a risky or expensive change reaches production. Instead of finding a security issue after deployment, scan the infrastructure in the pull request. Instead of discovering an enormous bill at month-end, estimate cost before merge. Instead of relying on a reviewer to remember every standard, express repeatable rules as policy. A guardrail is not simply a roadblock. A good guardrail gives fast, specific feedback. It explains what failed, why it matters, and how to correct it. AI can summarize findings and propose compliant alternatives. Deterministic policy should enforce non-negotiable controls. This creates a balanced model. AI assists, policy decides, and humans own exceptions. The first high-value guardrail is financial visibility before deployment. Cloud cost should not arrive as a surprise after the architecture is running. When infrastructure code changes, a cost engine can estimate the likely monthly difference and attach the information to the pull request. AI can explain the drivers in plain language. More nodes, a larger database, expensive storage, cross-region traffic, or an idle GPU. The engineer sees financial impact while the design is still easy to change. This is FinOps shifting left into engineering. It does not mean choosing the cheapest option every time. Reliability and performance still matter. It means making cost an explicit design dimension alongside security and availability. A useful review asks, what does this change cost? Which outcome justifies it? And is there a lower cost design with the same result? Prediction creates visibility. The next step is enforcement, where the pipeline stops a change that violates an agreed boundary. This pull request contains an automated cost gate. If estimated spend exceeds the agreed threshold, the merge is blocked or escalated for approval. Notice how this changes behavior. Cost is no longer a finance-only conversation weeks later. It becomes part of everyday engineering. A production service may have a different limit from a development environment. A temporary experiment may require an expiry date. A critical expansion may be allowed through a documented exception. AI can explain the increase and suggest alternatives such as right-sizing, scheduling non-production resources, changing storage tiers, or selecting a different scaling model. But the organization defines the policy. The purpose is not to prevent innovation. It is to prevent invisible, unowned spending. This is especially important for AI workloads because GPU resources can accumulate cost quickly even when useful computation is not happening. GPU infrastructure can be extremely valuable and extremely expensive. Research referenced in our planning highlights idle GPU waste rates in the range of 40 to 60% in some environments. The exact level varies, but the engineering lesson is universal. Allocation is not the same as utilization. A GPU may be reserved while waiting for data, blocked by a pipeline, running an inefficient batch size, or sitting active between experiments. Teams need workload-level metrics, queue visibility, scheduling policy, and clear ownership. AI can detect unusual idle patterns and recommend consolidation or shutdown, but automated actions must consider checkpoints, shared workloads, and service commitments. The goal is not maximum utilization every second. The goal is useful work per unit of cost, with acceptable performance and reliability. Once AI infrastructure becomes a major line item, cloud architecture and model economics become inseparable. This slide visualizes a scenario where AI and GPU compute represent 35% of the cloud bill. Treat that percentage as an illustrative planning signal, not a universal benchmark for every company. The deeper point is that AI costs are no longer hidden experiments. Training, inference, vector storage, data movement, model monitoring, and high-performance compute can become material business expenses. Engineers, therefore, need unit economics. Instead of asking only for the total bill, ask for cost per training run, cost per 1,000 requests, cost per successful task, or cost per customer outcome. Those measures connect engineering choices to value and expose waste that a monthly total cannot. FinOps for AI requires tagging, workload ownership, budgets, utilization metrics, and architecture choices that match demand. Cost guardrails protect the budget, but the same shift-left pattern can protect security and compliance before deployment. In this workflow, every infrastructure change is scanned automatically. The system checks policy, secrets, misconfiguration, and compliance requirements before merge. AI can summarize findings, group duplicates, and propose a safer configuration. Deterministic scanners and policy engines provide the enforceable evidence. This combination is stronger than either component alone. AI improves understanding and remediation speed. Policy ensures critical rules do not depend on a persuasive explanation. The scan must also be contextual. A public endpoint may be acceptable for one service and forbidden for another. A secret should never appear in source control, regardless of context. Results need severity, ownership, and a clear route to resolution. Most importantly, security automation should live inside the developer experience, not appear as a final audit. When secure behavior is the easiest path, teams move faster and avoid painful surprises later. The 3 a.m. bill shock is a memorable example of delayed feedback. A resource scales unexpectedly, a test environment stays active, or a compromised credential begins creating infrastructure. By the time someone notices, cost has already grown. Prevention requires layers. Start with budgets and anomaly detection. Add ownership tags and expiry policies. Restrict who can create expensive resources. Monitor usage continuously. Automate safe responses for well-understood cases, while escalating uncertain situations to a person. AI can correlate a spending spike with deployments, traffic, and resource changes to provide context. The goal is not merely to send another alert. It is to explain why spend changed and recommend the safest next action. Cost, security, and reliability are connected. A complete shift-left workflow brings all three into one delivery path, which is exactly what the next slide shows. Here is the complete Pillar 2 workflow. Code enters the pipeline. The AI cost check estimates financial impact. The security scan identifies misconfiguration and exposed secrets. The policy gate evaluates non-negotiable organizational rules. Only then does the change move toward deployment. Each stage produces evidence, not just a green or red icon. Engineers should see what was checked, which policy version was used, and why a decision was made. Exceptions should be explicit, time-bound, and auditable. This workflow creates speed because problems are discovered while the developer still has context. It creates trust because AI suggestions are surrounded by deterministic controls and accountable approval. We have now used AI to generate infrastructure and guard delivery. But the real cloud journey begins after deployment. Day 2 operations is where incidents and customer impact appear. That brings us to the third pillar. Pillar 3 is autonomous Day 2 operations. Day 1 is deployment. Day 2 is everything that follows: monitoring, scaling, patching, incident response, performance tuning, backup, recovery, and continuous improvement. An autonomous operations loop has 4 stages. Observe the system. Correlate signals into context. Decide within defined policy. Then act, validate, and learn. Low-risk, well-understood fixes may be automated. High-impact or ambiguous actions should be recommended to a human. The goal is not 0 people. The goal is 0 unnecessary toil. Engineers should not repeatedly perform the same safe action at 3 in the morning when the system can detect, execute, verify, and record it reliably. To understand why this matters, we need to look at one of the largest problems in modern operations: alert fatigue. Modern platforms can produce thousands of alerts from metrics, logs, traces, security tools, cloud services, and application components. More alerts do not automatically create more awareness. When every signal looks urgent, engineers spend time sorting noise instead of restoring service. Duplicate alerts can describe one underlying failure. Secondary services may complain because a dependency is down. Static thresholds may fire during normal seasonal behavior. The solution is not simply deleting alerts. It is improving signal quality, ownership, context, and correlation. Each alert should answer a useful question. What customer or business outcome is at risk? What changed? And who can act? AI can group related events and build a timeline, but it needs reliable telemetry and service relationships. The next image shows the transformation from raw alert volume into a manageable incident picture. Imagine 10,000 raw alerts entering the system. Many are duplicates, symptoms, retries, or downstream effects. An AI correlation engine groups them by time, topology, deployment history, and behavioral pattern. The output is not 10,000 notifications. It is a small set of prioritized incidents that a team can understand and own. This is where AIOps creates practical value, turning signal volume into incident context. But the 5 incidents must remain explainable. Engineers need to see which alerts were grouped, why they belong together, and what evidence supports the priority. Incorrect correlation can hide independent failures, so confidence and human review matter. The strongest systems combine machine learning with service maps and operational knowledge. That leads to the technical core of this sequence, combining language models with graph relationships to find the likely cause. Logs contain words and events. Metrics show numerical behavior over time. Traces show how requests move through services. A language model can summarize these signals, while a service dependency graph shows which components connect to which. Suppose latency rises in a payment service. Logs show connection failures. Traces show delays beginning at a database call. The graph shows which downstream services depend on that database. A recent deployment appears on the same timeline. The system can now explain a likely chain of failure instead of presenting isolated dashboards. The word likely matters. Correlation is evidence, not certainty. The interface should show confidence, competing hypotheses, and supporting signals. The engineer validates the conclusion before a risky action. Once context is assembled, it can be delivered in a form teams already understand. One actionable incident ticket. An actionable incident ticket should explain what happened, what is affected, the likely root cause, the supporting evidence, and a recommended next step. It should include the deployment or configuration change that may have triggered the issue, the services affected, and the confidence behind the hypothesis. This removes the first exhausting phase of incident response, collecting context from multiple tools. The recommendation might be to roll back a deployment, restart a failed component, adjust a connection pool, or investigate a dependency. The action should never be applied blindly. The ticket must show risk, required approval, and a verification plan. After action, the system should confirm whether latency, error rate, and customer impact improved. That closes the operational loop. With strong evidence and safe boundaries, the platform can begin preventing impact before users notice. Proactive remediation changes the timeline. Instead of waiting for a service to fail, the system recognizes a familiar degradation pattern and acts before the user impact boundary is crossed. For example, database latency may be rising because of a known query pattern or an exhausted connection pool. The platform predicts the risk, selects an approved runbook, applies a bounded fix, and verifies that health returns to normal. Safety comes from constraints. The action should be reversible. The blast radius should be limited. Evidence and decisions should be logged. If confidence is low or impact is high, the agent should escalate rather than act. This is how autonomy earns trust, not through unlimited freedom, but through predictable behavior and transparent validation. When designed well, proactive remediation reduces downtime and operational toil. The next slide summarizes the impact organizations are pursuing. This slide brings the operations story together. Research referenced earlier reports that leading AIOps implementations can achieve very large reductions in alert noise and meaningful improvements in mean time to recovery. The visual highlights 95% less noise and 70% faster MTT are as upper-end outcome examples, not automatic guarantees. Results depend on telemetry quality, ownership, operating maturity, and the incidents being measured. The practical target is clear: fewer meaningless interruptions, faster understanding, safer action, and better reliability. Do not begin with a percentage. Begin with a baseline. Measure alerts per incident, time to identify the cause, time to mitigate, automation success, rollback rate, and customer impact. AIOps should produce operational outcomes, not only impressive demonstrations. Even when automation becomes powerful, the most important question remains human. What should engineers learn to stay essential? To stay essential, focus on the skills that define and govern systems. First, system design. Understand resilience, scalability, data flow, failure domains, and trade-offs. Second, security boundaries. Know identity, least privilege, secrets, network trust, and data protection. Third, architectural judgment. Choose the right service for the requirement, not the most fashionable tool. Fourth, human oversight. Set goals, validate evidence, manage exceptions, and remain accountable for impact. AI can generate options, but engineers must know what good looks like. Build the habit of asking for assumptions, alternatives, risks, and verification steps. Learn enough FinOps to connect architecture to cost. Learn enough observability to connect symptoms to customer outcomes. The future engineer is not removed from a system. The future engineer operates at a higher level. The next slide compresses the entire model into 3 memorable verbs. Here is the complete model. AI generates the initial infrastructure and documentation. AI guards delivery by explaining cost, security, and policy findings. AI triages operations by correlating telemetry and recommending action. Above all 3 stages sits the human architect. The human defines intent, sets boundaries, approves high-impact changes, and owns accountability. This separation matters. Generation is creative, and probabilistic. Guardrails should be enforceable and repeatable. Triage is evidence-driven but uncertain. Human governance connects all three. Use this model to evaluate any AI cloud tool. Ask which stage it supports, what data it accesses, which action it can take, how the result is validated, and how a person can override or investigate the decision. If those answers are unclear, the system is not ready for production autonomy. AI should extend engineering capacity without hiding responsibility. The visual shows a narrow, fully delegated zone and a much larger area of human supervision and judgment. Research cited in our planning indicates that developers may use AI across a large part of their work while fully delegating only a limited share, sometimes reported as 0 to 20%. That difference matters. Using AI does not mean surrendering ownership. AI may draft code, analyze data, provision a test environment, or scan configuration. A person still reviews accuracy, validates security and compliance, approves risk, and accepts the business impact. The percentage varies by task and organization, so treat it as a collaboration principle, not a fixed rule. Delegate repetitive, reversible, well-observed work first. Keep ambiguous, irreversible, or high-impact decisions under stronger human control. This is not humans versus AI. It is humans designing better systems with AI. Now the entire journey is visible. Stage 1 is the YAML operator, manual, reactive, and surrounded by repetitive configuration. Stage 2 is the intent auditor, validating AI-generated infrastructure, enforcing policy, checking cost, and governing risk. Stage 3 is the system architect, orchestrating agents, designing multi-cloud boundaries, and focusing on reliability, economics, security, and customer outcomes. This transformation does not happen by abandoning technical depth. It happens by using technical depth at a more valuable level. Continue learning infrastructure as code, but also learn architecture. Continue learning automation, but also learn controls. Continue learning observability, but also learn how decisions affect users and the business. AI amplifies the engineer who can define the right problem and judge the answer. Spend less time repeating syntax and more time designing what matters. One final message remains. The future belongs to engineers who design the boundaries. Build a cloud, but do not stop at provisioning resources. Orchestrate the AI that generates, guards, observes, and improves the platform. Keep humans accountable. Make every automated action explainable, reversible, measurable, and secure. If this video gave you a clearer roadmap, subscribe to TechWithKoushik for more practical technology and career content. Like the video, so more cloud engineers can discover it. Share it with your DevOps, SRE, platform, or cloud architecture team. And comment with the most tedious cloud task you want an AI agent to handle. Before you leave, remember to download the free PDF study guide using the link in the video description. It summarizes the key concept from this video and gives you a convenient reference for later revision. Remember the journey, from syntax to intent, from alerts to action, and from YAML operator to system architect. Do not compete with AI at repetition. Use AI to amplify your judgment, architecture, and impact. Thank you for watching Tech with Kaushik. Keep learning, keep building, and I will see you in the next video.